Welcome back to class 11 in thermodynamics. Now we're going to do an example 312 out of Borgnakke. And I'm trying out a new microphone. Well, I've had it before, but it has this problem, this Yeti that puts a little volume thing up in the top left. I think it's obscuring your screen. It probably is. So I'm going to get like a little add-on I need to do to get rid of this stupid thing. So here's the problem. A cylinder fitted with a piston has a volume of 0.1 cubic meters, and it contains 0.5 kilograms of steam at 0.4 megapascals. The heat is transferred to the steam until the temperature is 300 degrees Celsius, while the pressure remains constant. And I didn't write down what we were supposed to find. Unfortunately, I should have included it on there. But we will need to do a find the heat that's transferred to it, find Q, and the work that's transferred between. And these are between states 1 and 2. All right, remember that we're always looking at what happens between things. So this was the constant. The pressure remains constant, so therefore we have an isobaric process. And they've already kind of showed you what the results are going to be, but let's pretend we didn't see it. Let's pretend. Okay, so we're going to, first we're going to try to find out what happens at state 1. So I'm going to write down what's state 1. Not a bad idea. They told us that the did they ever tell the pressure was a 0.4, so the P was 400 kPa, same thing as 0.4 megapascals. And they didn't tell us the temperature, but they did tell us that the volume was 0.1 cubic meters and the mass was 0.5 kilograms. Therefore, let's see, I don't use that simple, I use that one. We could take the volume divided by the mass, or 0.1 divided by 0.5 should be 0.2, right? Can I do that in my head? Look at me. Ooh, look at the big brain on Brad. That was a Pulp Fiction reference, by the way. You need to watch Pulp Fiction if you never watched Pulp Fiction. We should have like required movie watching for Dr. Deal's class. We did say, okay, this is heat is transferred until it's okay. So T2 is going to be this thing right here, the 300 degrees Celsius. So that's still state 1. So here, this is also state 1, and that's going to be a constant state 1, right? Okay, no, the volume's going to change. Okay, so this is a piston, so it's not a closed cylinder. Yeah, okay. So the volume, this will change. So this is V1. So I'm going to go to table probably B12, right? That's the pressure indexed one. Let's see if we can find my book. It's right behind me. It's too bad you can't see a picture of me. And they stopped the video capturing tools that they have for us here at UHart. It used to have an extra camera on there and you could capture both things at the same time, but now with Kaltura, well, you can capture them. They don't put picture in picture. They just capture 2 separate videos and you have to merge them yourself. And this is just exciting stuff that I know that you wanted to know about. All right, so here you go. We'll start off with here and we'll find what the properties are. So the specific volume, we come down and we want to find 400. And here's the specific. Here's you can't see the header at the top, but here's the for the fluid, and here is for the gas. And we know, lo and behold, we are in between these two. So we are some type of a mix, and the saturated state underneath the vapor dome at 400 degrees Celsius. So we're going to write all that stuff down so you can just trust me that I got it right off the right thing. So you go at P is equal to 400 degrees Celsius. We get a VF equal to 0.001084 cubic meters per kilogram. and a VFG equal to 0.4613 cubic meters per kilogram. Okay. And something we're going to do, by the way, we're going to demonstrate the enthalpy, right? We might as well capture some information along the way. And we're going to do it kind of two ways, just to demonstrate that enthalpy is a shortcut. We're kind of proving it to you. So the first thing I would do with this is to find out what the quality is going to be at this state. That was the reason why I wrote this down. And this is your mindset, right? So here's the problem-solving strategy: is we figure out what the quality of the X is going to be first, and then we can get the other properties. All right, so we used this information they provided just so we could get quality. That's our purpose in doing this. So we take that V is equal to VF plus X times VFG, and we plug in what we know, 0.2 is going to be equal to 0.001084 plus X times 0.46138. And we're going to get that the X is equal, wrote it down somewhere, 4.4311, or in other words, 43.11%. Right now, while we're here, let's also find UF and UFG. So we come back into here under the 400, and right there is, to get it, no, right here under the pink, yeah. There's UF and here's UFG, so 604.29 and 1949.26. 604.29, and these are kilojoules per kilogram. And this one is going to be, where'd you go, for 1949.26 kilojoules per kilogram. And so I'll write this over here, right? So it's still going to be the same thing. It's going to be U. So U is going to be equal to 60, is it a 4 or 9? I can't read my own writing. I think it's a 4. 29 plus 0.4311 times 1949.26, and we'll get a U equal to 1444.6 is good enough for sig figs, right? But forecasting things to come, we will also look up our F, HF, and HFG, right? So here's the enthalpy, and this actually, in our book, is on the facing page right here, right? So for enthalpy, HF, and HFG, and we come down to 400 right here. So here's HF, and here's HFG. By the way, I forgot to write down what the temperature was. It's probably always good practice to do that, but I didn't do it. But it is interesting because we're going to raise it to 300 degrees so you can see how much we raised it. So there you go. So I'm going to write down the 604 and the 2131.81. And you can see that it's not a lot different right there, right? So this was 604.29, coming back here. This should be a little bit more of 604.73. So that's a good idea to closely relate the internal energy and the enthalpy, because this is just this plus a little something more. Yeah, that was kind of funny that I said that, wasn't it? Maybe, no, all right. So I'm gonna go 2,100, whoops, and 33.81. Once again, just a little bit more than that. So the H is going to be 604.73 plus 0.4311, and then go 2,133.81. And that's going to be equal to 1,500 and 24.6 kilojoules per kilogram. And somewhere up here, I should have wrote that Tsat was equal to 143.63 degrees Celsius. All right, so I have all my information for state 1. Let's go to state 2. Now, so it's going to be the temperature at state 2. They said it was 300 degrees Celsius, and P remained at 400 kilopascals. So this one I can just look up in table B.1.3. Well, I mean, I probably should look, but I already know, because at this pressure, the saturation temperature is here. So if the temperature is larger, it must be superheated. So I can flip over here and go to the 400. Yeah, where's 400? Okay. Here's pressure. Did I say 400? Yeah, 400. And then we can go to temperature 300. And we can get our specific volume. We can get our internal energy. And we can get our enthalpy. So it's a good chance that this is going to equal this plus that times that. I might actually check that out. I don't know. I think that's true. It might be, and so that might just be like a simple thing to do. But let me double check. So here's our specific volume. It's going to be 0.65489 cubic meters per kilogram. And then our internal energy, and this, we'll call that 2. And 2, we'll put 2's everywhere. Make sure it's state 2. It's going to be 2804.81 kilojoules per kilogram. And then our enthalpy, 2, is going to be 3066.75 kilojoules per kilogram. Now, the work done, so they wanted the work, so find the work that's done between 1 and 2. It's going to be integral between 1 and 2 of the pressure times the volume. But we know this is going to be a constant volume process. So if that's the case, we go P times V, let's call it V2 minus V1 times the mass, right? Because they weren't, I gotta be careful, they weren't particular. I was gonna say specific, because that would have been a pun and hilarious. But they weren't particular about what kind of work, but we can assume that they didn't mean work per mass. So we'll multiply it by mass. And if we do that, we get, so I like to go in base units, 400,000, that's going to be Newton per square meter, newtons per meter squared, and then multiply it by this cubic meters per mass. And so that's going to be 0.65489 minus our 0.2 from state 1, and then multiply it by our 0.5. And so for work between 1 and 2, we get 90,968, which is a Newton meter, just the way that works out, right? Which is also going to be 90.97 kilojoules. If you go internal energy now, well, no, let's write our big question. The big equation that we've been using is U2 minus U1 is equal to Q12 minus work 12. So this is heat in and this is work out. And so we could say that if we wanted to get the heat between 1 and 2, we would take U2 minus U1 and add the work that went between 1 and 2, which would be let's write it over here, U2 minus U1 times the mass plus the work between 1 and 2. So I'll write that here, 2804.81 minus, come back up to here, 1444.6 times 0.5, because it's times the mass, right? And these are kilojoules per kilogram, and we multiply by kilogram so that we're compatible with this, and we add in 90.97, and what we're left with is 771.1 kilojoules. All right, so there is the work and the heat, but let's go ahead and use the enthalpy, right? So the enthalpy is actually all this stuff put together. And so a shortcut for this using enthalpy, it's just going to be H2 minus H1 times mass. So I got to tell you, I went years without ever using internal energy because I was always dealing with systems, and I just dealt with enthalpy all the time. So it's going to kind of replace a little bit that, but we might run into other circumstances where we want to know the internal energy of a particular chunk of mass. But if we're dealing with a system, quite often it's just going to be enthalpy. So 1,524. And then times 0.5. And what you're going to get is 771.1 kilojoules. It's the same. Same. There you go. All right, so we are done with the second video of class 11. We'll have some more coming up. We're going to deal with specific heats. Really important thing to know about. Talk to you soon.